thanks for the invitation to come here. It's always cool to come visit Bristol. Here quite a lot, working with various people. So this is work I've been doing for the last few years. I'd say mostly with Ashley Montanaro and Dan Shepherd, who are sort of locals. And lately with a cast of a lot of people, including Austin London and Tim Ralph from the University of Queensland, and, well, a cast of many people at Google and NASA. So, as Pete just said, I work at UTS in Sydney, and I also work for the Centre for Quantum Computation and Communication Technologies in Australia. I should also say that Winnie was my first year physics tutor, so like everything that follows is Winnie's fault.
No, all the good things. He was an outstanding student, actually. He was one of the best students in the class.
Okay, so as we've just heard from Winnie, actually, I mean, one of the big challenges over the... It's actually really great to hear that talk in that that was a talk like entirely about scaling up. Like, how do we go from like having basic interactions of, you know, 1 or 2 qubits and moving to building a device which is like really, really big. And the challenge of this talk, and the challenge for theorists for the most part, is to work out how we can, as quickly as possible, develop applications and demonstrations for people who are working on these scaling up technologies to demonstrate the capacity of what they can actually do in, you know, the shortest amount of time possible. So, I mean, there's been tons and tons and tons of talk about quantum supremacy in the press in the last year or so, and you know, this is basically my take on it. What we're trying to do at the moment is to try and identify classes of, you know, quantum problems where, say, the quantum runtime, does that work? Sort of, you know, is totally reasonable, whereas classical runtime is totally and utterly unreasonable. But bearing in mind that our quantum device is actually going to have sort of a maximum amount of time it can run for, or a maximum number of operations before it just, you know, dies. And bearing in mind that the maximum digital runtime is much, much, much longer than that. So the goal is to try and find sets of applications where we can unambiguously beat the best that you can do with a classical computer. And when I say unambiguously, I mean it isn't just a consequence of lack of imagination, but rather it's a true demonstration that the quantum computing model is much more powerful. And you know, there are really key issues that are involved with this problem. You know, the first one is, are quantum computers actually more powerful than classical computers? So this might seem a little bit absurd to this audience, but from a computer science perspective, this question is really not settled. And the evidence for it, you know, we're building, we actually have quite a lot of evidence for it, but as is the problem with much of computer science, proving definitive separations between computational models is really, really difficult. And that, you know, hasn't been done for quantum computing. It's unlikely to be done, as you point out, while many of the outstanding challenges in complexity theory remain. But it is something that you always have to bear in mind. So the best statements we're going to make are always going to be relative to some complexity theoretic conjectures. In fact, they'll only be relative to a few complexity theoretic conjectures. All right, so then we hit the second problem. You know, for which computations do we expect the quantum and classical runtimes to dramatically diverge? And then finally, which I think is a really, really big question, is can we achieve quantum supremacy without actually the full machinery of fault tolerance? So when we're talking about separation between quantum and classical computing, we're talking about asymptotic separations, right? So these are things about scaling with qubit number or in the problem size. We currently don't really believe that quantum computers can really scale without using error correction and, to some extent, the full machinery of fault tolerance. So the question is, if we can demonstrate separations, can we really do so without actually reaching for the full machinery of fault tolerance in order to see those separations? I think this is a really big, outstanding question. All right, so these can be summarized by some very basic theory goals. The first one is, you know, identify some applications. I didn't put that up there. And then minimize the gate count and qubit count, get them as low as possible while still showing a separation over classical computers. understand the influence of errors and then mitigate those errors. These are kind of the goals which are very much theoretical goals. And they can best be achieved by working closely with experimentalists as well. I should say, the sort of region we're punching for is something like this, right? So we're trying to aim for that point on the curve and to prove that that is something which actually, can exist in nature. Okay, and I've kind of put down a few numbers here. That's kind of fortuitous. So the Google proposal for demonstrating, computation beyond that which classical computers can do is punching for around 49 qubits and trying to show that, you can tick many of these boxes by building a device of that size. All right, so, what is the main goal or trick that we're using to demonstrate all of this? So the main theoretical tool that everyone's been using to look at this is this idea of random circuit sampling. So the idea, seems really basic, but ends up being a bit more complicated as you dive into the details. But the goal is simply to, basically choose some random circuits with some properties. Okay, random quantum circuits, and you're going to output samples from that circuit with, some probability as defined by the circuit. It's a quantum circuit. It'll output samples with some probability. We'll call that probability P of X. And the idea is to bound the complexity of this process by simply studying the properties of P of X. Now, that seems like overtly simplistic because it is. Normally what we do when we're looking at quantum algorithms, we actually identify a more clear task than that. But what we're trying to do is to leverage that we actually can actually identify for certain classes of circuits a lot of the properties of these probability distributions. And we're going to study the properties of probability distributions in order to try and build a separation out of that. So the hope is that if these probability distributions are complex enough, then classical computers can only ever simulate sampling by computing that output probability. And that task is typically really, really hard. And to produce a really high accuracy output, really high accuracy computation of that output probability. And the more physical intuition is that by looking at random circuits, they're kind of great in that they build up entanglement really quickly. Okay, so they quickly become very complex. If you look at the Google paper, they talk about this as they very quickly become quantum chaos. They have signature of quantum chaos. So in those sort of systems, we don't have a lot of simulation methods other than directly computing those output probabilities. And then this leads to very, very long classical runtimes on those computations. Now, what I'm talking about, it goes a bit beyond just saying it takes a long time to compute these things in the best classical algorithms that we know of, because you can always think we might come up with a better algorithm than that. But that's just sort of the vague intuition. These things get big and complicated very quickly. So you might think, why not something with a bit more structure? The problem is that once you start adding more structure to the system, to a quantum system, there's a lot more symmetries you can exploit in an algorithm. So random circuits are great because of the lack of structure. Unfortunately, this also means they're not so great for finding, interesting applications, because algorithms themselves typically, need a lot of structure. All right. So, okay, this idea, the idea to look at random circuits for this sort of task goes back to Aronson and Archibald. Their boson sampling proposal established a potential advantage over classical computing for sampling from random linear optical networks, and importantly, and really importantly for this entire analysis, is that they rule out classical algorithms for outputting samples from the quantum system up to a well-defined notion of distance. So there was a lot of earlier work in the field on studying the properties of the output probabilities of quantum circuits and trying to define separations between quantum and classical computers. However, they always worked in a regime where we didn't have well-defined. All the results we had were not based on a nice notion of distance between what the classical computer is trying to output and what you might, what you've ideally got your quantum computer doing. Okay? So what's great about that is it's commensurate with our theory of fault tolerance. and it allows for you to talk about things like, we're going to allow for implementation errors in the system as well. So all of these things can be supported under this theory and under this style of proof. Okay, and in 2015, actually Dan and I adapted this boson sampling argument to the quantum circuit model. And the way that we did that was by studying a class of circuits that people call IQP circuits. In a sense, what we managed to do, well, was a few things. It was important to move it to the quantum circuit model because now it can sort of use the full machinery of fault tolerance and error correction in sort of, thinking about building these circuits. And that's conceptually quite an important thing because this is a bit less clear in the boson sampling model how errors will work. I should say also, the other advantage of moving to this model was that it allowed us to actually, what I didn't mention before is the boson sampling actually relies on 2 unproven conjectures. Actually 3 unproven conjectures. One of them we're just going to take as a given, which is that complexity theory behaves the way we think it should. One of the conjectures is that, that the average case complexity of the permanent problem is as hard as the worst case complexity, and the other is about the statistical properties of permanence of Gaussian matrices. We managed to prove the equivalent of that conjecture for the IQP model. It turns out to be actually quite easy in this model, and it's quite a lot easier to analyze in circuit models typically than it is actually for bosons, which is good. Okay, the other big advantage of, well, the big, I guess, result of that work was that it's actually really easy to generalize. And there's actually been a raft of generalizations over the last year or so since we put this paper out. Probably the best known one of these is one that people proposed last year. Okay, let me try and talk through the physics of this a little bit. None of this will have anything to do with superconductors, so because I don't know that much about that. I'm a computer scientist, sort of. Actually, I'm making a face. Alright, so Google's proposal was to try and, punch for quantum supremacy by building an array of 7 by 7 array of superconducting qubits. Okay, so this array has some limitations. All the interactions are going to be nearest neighbor, which is, I guess, pretty normal for a physical system. There are some limitations on when you can apply C-phase gate. So you use C-phase gates as entangling gates in this architecture. They can't, at the moment, do 2 C-phase gates sort of on qubits which are next to each other at the same time. So you sort of do a C-phase gate, you have to leave a gap around it when you're doing that C-phase gate. So their idea is basically apply a bunch of Hadamards to your qubits. Later is totally quitting. You apply a whole lot of Hadamards to all of your qubits. These dots here are the qubits. It's a bit hard to see, I guess. Then you do a layer of entangling operations. Then you apply a set of random 1 qubit gates, and then a layer of entangling operations, and so on. So basically, all these single qubit gates are just T square root of x square root of y gates. So these, together with Hadamard, actually form a universal gate set when you add the C-phase gate. So basically, their goal is to show that, what they're basically arguing is that once you get above square root and depth, and for them there's a few constants, so they say roughly about 35 layers of gates in this model should be enough to sort of considerably outperform the best classical algorithms running on supercomputers for simulating the system. I should also say that they sort of aiming for around 99.9% fidelity in all their operations across this architecture. So you can think that gets you to about 1,000-ish gates before things aren't really making a lot of sense anymore in this system. Okay. And the details of that you can find in this archive paper. Alright, so I'm going to try and give a bit of intuition as to why people think this is actually like something which is hard to classically do. And to begin with, I'm going to give a brief summary of quantum computers, because we haven't heard enough about that yet today. Okay. So, basically all quantum computations work like this. You input some classically easy to describe circuit and an input state, and you output strings of bits with some probability defined by that circuit. That's what quantum computers do. Entangling gates typically be active between the qubits and gates that drawn from the universal gate set. So as I was saying, the way that we analyze this problem is to consider the complexity of the problem, the complexity of P of X for this problem. Okay, so sorry, there's a couple of slides which involve complexity theory, which, and I gather all of you are experimentalists, so it's a little bit painful. But fortunately for certain classes of circuits, the complexity of P of X is kind of well known and quite easy to study. We know that there's a hard upper bound on the complexity of this problem, which comes from, well, right back to the early days of quantum computing. And we know that this output probability can be sharp P or gap P hard to compute exactly, okay? And that's as hard as it gets. It can also end up being down here in P, and it depends entirely on the circuit class. For instance, if you choose a Clifford gate, this is probably like a Clifford circuit, this is computable in P. But if you're going to choose other things more generally, you can prove that this definitely will be that hard to compute. Importantly, we don't think quantum computers can compute their own output probability with very high accuracy. So the best we think we can do is to get an approximation, which is an additive error approximation to P of X. So one over polynomial approximation to compute this function. So why is it not very good? That sounds pretty good. One over polynomial seems pretty good. The difference is that P of X can sort of range from 1 on 2 to the n, up to 1, right? So 1 over polynomial approximation to that is kind of terrible if the answer is 1 on 2 to the n. So it's not a very good approximation to what these things can do. Now, the trick of all these random sampling problems is that actually what we're going to do is to add in a BQIT, an NP machine, basically, to our quantum computer, and then ask what could we do, could we then get a better approximation to this output probability? And it turns out that you can under certain circumstances. All right, so the next thing you need to know in order to understand this is that we need to know a little bit about another class of approximations for computing these probabilities. That's a relative error approximation. So relative error approximations are typically, a bit better than additive error approximations because, the scale of the error or the scale of the answer, changes depending on the size of the problem. Okay, so they're much more accurate when you have, exponentially differing scalings in a system, for instance. Now, it turns out, and it's not too hard to show, that there are classes of quantum amplitudes that stay what we call gap P hard, even with relative error approximations. And you can actually show that for a wide range of systems, and that actually underlies all these sampling problems. Such classes include linear optics, IQP circuits, universal load-up circuits, and many, many more. Okay, so that means that there are output probabilities of quantum circuits where if you have a relative error approximation, it's still really, really hard to compute. We don't think quantum computing can do it, but what you can end up showing is that there is actually an algorithm when you have an NP machine for free, which will allow you to get an approximation which is accurate for those things. That algorithm is called Subclass Algorithm. It goes back to the early days of complexity theory. And it was shown that this algorithm can give a relative error approximation for these for functions that are in sharp P. Like I said, this does not work for gap P hard functions unless they're quantum hierarchy collapses. So if you had a quantum simulator, you would be able to compute these functions. We don't think you can do that. That's kind of the main trick which is being used in all of these random sampling algorithms. Okay, there are a few conditions to make this algorithm work well, and that is that if there exists a sufficiently accurate, efficient classical sampler, and by sufficiently accurate we mean one which is accurate up to, say, a constant variation distance, which is like very, very reasonable for having a sample. And a sufficiently random unitary. So you can show the Subclass algorithm delivers a relative error approximation when you have sufficiently random, if these functions have sufficiently the right set of randomized properties. Okay. This can all be sort of summarized by this slide. All of these sampling type arguments come about from the following way. Firstly, you sort of identify some class of U where computing an output probability is sharp P hard or even gap P hard. Well, sharp P hard even up to a multiplicative approximation in the worst case analysis. So imagine this big circle is like something like that. And then what you want to do is that these are sufficiently random, and that they look sufficiently like, say, for instance, the Haar distribution. That's a fancy way of saying that is that this thing anti-concentrates, which means that there's a sort of, basically the output probabilities are all sort of quite small, so they're sort of like 1 or 2 to the n, but there's a bit of a variation to it, like a polynomial variation over the top of that. There's a little bit of structure to it, but it's not like completely uniform. And you also want that, for many instances of these problems, it stays sharply hard. So it's not just the worst case, but the average case. So what Stockmeyer's algorithm will deliver you is it'll compute well things that are in this little blob, and you also want things, you also want a high overlap between the things which are hard and the things which Stockmeyer algorithms will actually compute. Okay, what we can actually prove looks like this. This is why we need conjectures right now. So you can prove that there are sort of things which are sharply hard. You can prove that a large fraction of these things do actually anti-concentrate, but at the moment, we don't know how to compute that there's a high overlap between those two classes of things. Okay, and to give you a bit of a flavor of this, what I mean when I say that, is you can come up with statements like this. And this is from our paper in 2015. You can say that if the average case complexity of relative error approximations to either, say, the complex temperature isomorphic partition functions or the gamma degree 3 polynomials is sharply hard, then quantum computers cannot be efficiently classically simulated to within constant variation distance without a classical polynomial hierarchy. Alright, so that was a lot of words, and all that's really saying is that the output probabilities of these circuits, say these circuits, they actually can all be associated with an isomorphic partition function, which is something which is actually kind of easy to study. We know the complexity very well of those problems, and we can compute a bunch of things about the statistics of those problems too, which is what we did to show that and prove that theorem. Now, if we shift attention to, say, the Google proposal, what's going on there is that classical hardness is basically based on a similar argument, and there the output probabilities of these things, there's 2 assumptions that you need to make. First, one of them is actually like really heavily numerically investigated, is almost certainly true, which is that when you go to sufficient depth in this system, then these output probabilities actually anti-concentrate, which means the Stockmeyer's algorithm works well. And the second is that the average case complexity of complex partition functions, so quasi 3D isomorphs, are as high as their best case complexity. Okay, so those 2 examples, you can actually come up with many examples of this and analyze it. I don't know how, this is all probably a bit too small for people to see, but you can go through and start asking questions about, okay, I can identify circuits with these sharply hard output probabilities, and then analyze the statistical properties of these systems and see what they look like. And people have been doing that. Some interesting things of note are the constant depth circuits. Recently, there's been quite a few papers showing that, or arguing that constant depth quantum circuit sampling is hard for classical computers. And those arguments are basically built on extensions of the IQP sampling argument. And basically what they do, which I'll explain a bit more in a few more slides, is that they do measurement-based implementations of these circuits. And they show that there is under this measurement-based implementation, all the arguments can follow through nicely. And that there's a few technical things you have to check there, like on the output register, does the output probability sort of behave in the way that it should still behave? And people will basically be able to numerically investigate that and show that it actually behaves exactly the way you would hope it would. Okay, that brings me to, I guess the problem which is more of a concern for experimentalists. What you want to do is to find proposals like this and minimize the experimental cost of doing that. Okay, so if you go to the original IQP sampling proposal, you require something like n-squared gates, and they can be long-range gates, so they can be across the entire system, which is kind of scary. You can get that depth down to order log n with a universal gate set and a lot more qubits, the depth is, and you can show that the depth is order n with the 2D nearest neighbor architecture, which is still like really deep, right, for near-term devices. So that's a lot of gates and a lot of operations. So last year, Dan and Ashley and I went back to the drawing board a little bit, and we showed that you could still prove the same conjectures or prove the same theorems by moving to a sparsizing law, which reduced the number of interactions in these models and reduced the gate count considerably. So the new results require order n log n gates, so we basically knocked out a factor of n gates, which is actually a lot. And this leads to basically an order root n depth computation, which is nice. This takes something from being not really feasible in the near future to being something which is something people aren't going to really think about doing. And as I just said, there's been actually a few papers where this has sort of been improved further to constant depth, but that comes at a cost of adding many more qubits to the system. All right, so something I should have said is that these constructions, where we drop the depth down, you go from having these IQP circuits, which only have diagonal gates in the middle, to implementing them in a universal gate set. So you need to start doing swap gates and things like that in order to do this. So how do we prove the depth of these circuits? Well, first you prove that you can do sparse IQP sampling, so you do that. And then you can use an edge coloring algorithm to decompose the circuit into order log n partitions of simultaneous gates. So gates you can do at the same time. And then you can apply basically standard results on splitting networks to each one of those partitions and show that that can be done in depth, order root n depth with universal nearest neighbor architecture. So you do this partitioning and then you break that up into like a 2D nearest neighbor architecture via sort of standard, almost classical results. Okay, so what's kind of cool about this sort of construction? For the IQP circuits anyways, you can always prove that this leads to near optimal depths for this class of problems. So you can prove that you can see there are tensor network algorithms for computing the output probabilities of these circuits that run in time 2 to the d times d, where d is the depth of the circuit and d is, let's say, the diameter of the circuit. So in a nearest neighbor architecture, that means that if the depth were to go below root n, then there's going to be a sub-exponential time algorithm for computing those output probabilities. Okay? So it turns out for these sort of sparse IQP circuits, the corresponding partition functions it's believed that there is not a sub-exponential time algorithm for those partition functions. So if you assume that, then this is essentially optimal for this class of circuits. You should know that the Google proposal, the scales are basically root n, and this is slightly better than what we can show, but that's sort of been numerically investigated. So they shave off that log factor. So the question is, how low can you go, right? So if you're looking at this sort of class of problems which are sort of hard on 50 qubits, if you want to move to like a constant depth architecture, you need a dramatic increase in the number of qubits. Okay, so it's like a polynomial increase in the number of qubits. So literally that's 49 qubits there, and you end up with like around 2,500 qubits as being what you actually need to do to implement that in a measurement-based model. So yeah, for this class of problems anyway, once you get to these sufficiently sparse problems, you begin to really, really trade off depth versus number of qubits. So it could be the case that in various architectures this is a lot easier than this. For instance, you could imagine optical lattices or something like that, where you've got a lot of parallelism. This might be considerably easier than doing a whole bunch of gates. But this is something that, with details, people are going to have to work out eventually. All right, we're going to have to skip through this all pretty quickly. But this has all been very sort of good news stuff, but there is actually some bad news. And this we wrote a paper about last year, which is that precisely this class of anti-concentrating IQP circuits have a classical simulation under certain noise models. The particular noise model we studied is to use have depolarizing noise at the end of the circuit, which is like a measurement error. Now, it's important to remember that such circuits are a long way away from the thing you're actually aiming to implement. This is where I'm talking about false tolerance, all sorts of things like this. So say this is green light that we're trying to do. It is the case that these noisy systems are like diverging away from the class of things that you're actually trying to simulate. So the noisy thing very quickly will not be anything like the system you're actually trying to implement. Especially when you have a constant amount of error per qubit. So what we showed is that while this is sort of running away from the ideal system, there is actually a good classical simulation of that thing which is running away. So this is by way of saying you just have to be kind of careful in your analysis of these things. It could be that the physical situation, the thing you're trying to, you're actually trying to implement, the physical device you've made might actually have a good classical simulation, whereas the ideal device may not. So this is why you might really need error correction, which is what we did in the next thing, which is to show that actually for this class of errors and circuits, there is a semi-classical notion of error correction. So this is something which is sort of intermediate between fault-tolerant quantum computing and doing no error correction at all. So we're able to show that there's a relatively low-cost error correcting code which only acts on the description of the circuit and not really the qubits themselves. So there's no concatenation in this, which is kind of great. It's simply a re-encoding of the class of circuits you're actually trying to compute. So there's a bit of a cost in terms of qubits, but it's more like a constant cost instead of like quantum cost in terms of qubits, which is good. And that's a bunch of math, but I'm kind of out of time, so I won't go through all that. Finally, the last thing I should get onto is verification of these things. So the circuits that we're talking about are going to be really horribly complex, and we know that tomography on these circuits is not going to work. And in general, complete verification is really too hard for these to consider for these systems for now. But we showed quite a few years ago now is that, at least for the case of IQP circuits, you can generate two-party tests. So, as a client, I can test whether the people who are claiming they have a quantum computer are actually performing the computation they're claiming by using pseudo-random circuits and basically a cryptographic game where I challenge them to actually do something. This does not completely verify the circuit that I've been performing, but I can pretty easily check whether they're very far away from actually doing the computation they claim they're doing. And there's a few other things that people have looked at. So in the Google paper, they've looked at getting fidelity estimates from cross-entropy approximations, which is something which is a bit easier to do than actually computing your fidelity outright. And really recently, these constant depth architectures that people have been looking at actually do have a whole slew of techniques for actually checking actually work. Finally, there's a really cool paper by Scott Aronson and Li Chen, which I just thought I'd quickly advertise to say that you can kind of look at the complexity of these randomized circuits from a completely different point of view instead of focusing on complexity counting problems, which is what I've been talking about all day. You can use a slightly stronger assumption. And if you use that assumption, you also get out of it a nice sort of verifiable problem that you can easily check. That's the heavy output generation problem. It basically is sampling. So I just wanted to put that there as an advertisement, go and look at that paper, it's kind of cool. Yeah, that's kind of what we're aiming for, and thank you.